Chapter 4 focuses on a particular part of the cell, in particular eukaryotic cells, which are membranes. So we're going to look at membrane structure and function in this chapter. Here are our learning objectives. There are 7, and we will just march right through them. Starting with objective 1, what is the function of the plasma membrane? So the plasma membrane, as you may remember from the last chapter, it is the boundary around a living cell. So some cells have cell walls, but all cells have a plasma membrane that keeps the cytoplasm away from the outside world or from other cells. So the plasma membrane exhibits what we call selective permeability, which means substances can get in very easily, others with some difficulty, or not at all. So selective permeability is kind of like your house. Now, your house probably doesn't look like this, but it probably does in the sense that it's got doors and windows, and maybe it's got a garage or 2-car garage or something like that. And your house is selectively permeable to different types of objects. For example, if you want to get into your house, what do? Maybe you go through the garage door, maybe you go through the front door, but those doors are selectively permeable to you or anyone who's got a key to get in, assuming that you lock your doors. Windows are selectively permeable to light and heat, and they let in the daylight, they let in solar heat and warmth, which maybe you don't want, so maybe you'll draw the shades in the summertime to keep your heating bills down. And the walls are also selectively permeable to heat. If it's cold enough outside, eventually that cold air is going to get through inside your house and drop the temperature of your house. And in the summertime, the solar heat is going to get through your walls and heat up your house. So selective permeability means that some things, but not all things, can get into your house. So what's an example of something that couldn't get into your house? Well, imagine that you have just gotten a grand piano, and you're going to try and get it in through the front door. Your house may be selectively permeable against grand pianos. So in this house, for example, you probably want to take it in through the garage, one of these garage doors. Definitely not through the windows. That would not go well. Or let's say your house is selectively permeable against elephants. You wouldn't be able to get an elephant into your house because there's no doorway big enough to allow an elephant to pass into your house without significant damage to your house. So how does this work in the cell? The walls of your house are analogous to those phospholipids, which you remember are fatty acids connected to a glycerol molecule, and that third hydroxyl group is attached to a phosphate group. And what that means is that phospholipids have both that hydrophobic portion, that nonpolar part with just carbon and hydrogen, and they have hydrophilic regions. That phosphate group, since it's so polar, it loves water. So the fluid mosaic model says that the membrane is fluid, those phospholipids can flow, and then there's a mosaic of different proteins that are kind of embedded in it. Or it's almost like there's an ocean of phospholipids with occasional islands of protein that are embedded within that. So here's a cartoon that represents that. Here's that phospholipid bilayer, which self-assembles because the hydrophilic portions, the phosphate groups, are going to face the water, and the hydrophobic portions are going to huddle together and try and get away from the water. So that's what's represented here. And then embedded, the mosaic is the various proteins represented here as these purple blobs that may stick through the phospholipid bilayer. And these proteins have a number of functions, but maybe the most important in our analogy to the house is that they're kind of like the doors and the windows and the gates that allow things to get into and out of your house. In this case, the cell. So this image is just showing how on the outside of cells there's water, on the insides of cells there's water, and then you have this phospholipid bilayer with the hydrophilic heads and the hydrophobic tails, which if we zoomed in, we could look at all the atoms. This is what it would look like. You can see that you've got these long hydrocarbon tails. Here's one that's cis fatty acid because it's got that kink in it. And then there's this phosphate group that's like, hey, I love water. Give me all the water. But these phospholipids can kind of flow around on either side of that bilayer. So this lateral movement from side to side, that happens all the time, lots and lots of times. So 10 to the 7th times per second, that's 10 million times a second that these are able to flow laterally. But flip-flopping, going from one side of the membrane to the other, that's very rare. So rare that they figure it's maybe only once a month, which very rare indeed. It can happen, just not very likely to happen that a phospholipid is going to jump from one side of the membrane to the other. Okay, so how do molecules get through the plasma membrane? So remember that structure means that it's going to be selectively permeable, meaning that some things can come in and out and others cannot. So the plasma membrane, being selectively permeable, is going to regulate traffic into and out of the cell. So the lipid bilayer is permeable to nonpolar molecules, hydrophobic molecules such as hydrocarbons, so like fats and oils can pass through the phospholipid bilayer. Also gases can cross through the phospholipid bilayer, so oxygen gas, carbon dioxide gas, nitrogen gas, all of those can cross that lipid bilayer fairly easily and rapidly. But a polar molecule, like a sugar or an amino acid or something like that, cannot get across because it runs into that hydrophobic portion and it's like, nope, not letting you through. Water, even though the hydrophobic portion, by definition, is water-fearing, water is so concentrated that some water can get through that phospholipid bilayer. But if you need to move a lot of water, like in your kidneys are moving a lot of water, those cells, they need to have a little bit of help. I'll talk about that in a couple minutes. So remember I said that those membrane proteins are kind of like the doors and windows for materials to move in and out of the cells. So you've got these different proteins. Often they are grouped together or anchored together and they're embedded in that lipid bilayer. And it's the proteins that are going to determine most of the specific functions. Just like the door to your house is going to determine what kinds of organisms can get into or out of your house. Mosquitoes, no problem. Flies, if you leave your door open, no problem. Horse, that's another story. Elephant, no way. So proteins can kind of do the same thing where different shapes of molecules will fit into different proteins to get into and out of a cell with different degrees of difficulty or ease.